Now that I've let my hard drive speed up, let's go ahead and jump into it today. So today is our first day on chapter 27. We've kind of been hitting like a back-to-back kind of deal with 2 lectures per chapter. And chapter 27 is the last in that line before we hit 28. And then we're going to sit in 28 for quite a while, actually. But anyways, for today's material, so far we've been looking at all sorts of stuff with potential and electric fields and charge and conductors and what happens with all of that stuff. And every single time we've talked about those things, we've always been assuming that everything has been in equilibrium. Even in the cases that we're not in equilibrium necessarily, when we're talking about forces and there is going to be movement or something else like that, we're really limiting the cases on that. Every single time we're talking about conductors specifically, we have been at equilibrium. And that's really important, right? Because every single time we were talking about those things, we said, okay, well, every time I put excess charge on a conducting surface, all of that charge is going to be staying on the outside surface of that conductor. I can have, if I have a hole or something inside, I can have some charge on the inside, but only if I put another charge in there, and only to make sure that the electric field inside of that conductor is 0. And that is going to remain to be true in equilibrium. But the equilibrium point is a point that we kind of assumed, and I said it once, and then we didn't talk about it again for quite some time, but now it's becoming a little bit more important because we're going to be looking at the case where we don't have equilibrium, where we're applying some potential difference to a conductor and what happens because of that applied potential difference. So we've actually already looked at a scenario kind of similar to this one. Before I jump into the new material for today, I want to remind you of the last lecture. We had a problem where we had 2 metal spheres, and one of them was charged up and one of them had no charge on it. And when we connect that metal wire between the two, for that brief moment in time, we actually weren't at equilibrium. Right, for a brief moment in time, we had a lot more charge over on one side, and we had a conducting surface, and the charge was not spread evenly across that conducting surface. The potential was not uniform across that conducting surface. And what happened, we saw a flow of charge to the other conductor. So let's talk about that flow. We're going to start this discussion today by talking about what we call current. So every single time we have a conductor at equilibrium, we're assuming that we've got something like what we see on the left here, where the electrons are real particles that have a thermal energy to them, that have a temperature to them, and because of that, they're actually not just sitting there floating on by waiting for something to happen. They're actually constantly bouncing around to every which direction, right? Something like this. Very, very fast, bouncing back and forth between all of these different, we're going to call these ion cores. But remember what's actually happening here. When we're talking about something like a metal or anything like that, we have a band structure to them. So the inner electrons of every single atom are going to hug close to those atoms. They're not going to move, and all the atoms are in fixed locations. But the upper 2 or 3, the covalent electrons, are allowed to freely move back and forth throughout the entire metal. They're not tied down to any one particular location. So they're going to keep bouncing around until they get really close to one of those atoms. And once you get close enough, then you're much closer to the electrons than you are to the atom itself, and they'll bounce off and go somewhere else, right? So they're not just going to collapse into the positive charge and be off on their way. They're going to bounce off of it and continue on their path. So that's fantastic. And what we see is that over the entire conductor, even though every single charge is moving in every which way, the net motion still comes out to be 0. It's a bunch of random motion, but when you normalize randomness, you get back 0, right? If I let all of these different particles move in every which way, on average, they're not actually going to move. So what happens when we apply some sort of potential difference? How might we do this? Well, one of the easy ways to do this is if you take any sort of battery or something else and hook it up to a conductor. That applies a potential difference. Now, we actually have an electric field inside of the conductor. So every single time we're talking about putting an excess of charge on a conductor or something else like that, that is stored on the surface to make sure that the electric field inside of the conductor is 0. But if we are not in equilibrium, if we have an applied potential difference, then we will get an electric field inside of that conductor. But now what happens to that electron? Well, it doesn't stop going through all this random motion, right? It's still bouncing around in every which way. However, now it has a constant acceleration going against the electric field, right? That's what the force does. Now, keep in mind that I have been talking about electrons this entire time. And it's mostly what we're going to focus on, because that's the most common type of current that we're going to end up seeing. But we can have other types of charge moving as well. It's just we'd have to have things like plasmas or something, and that much more complicated, not something we're going to worry about. If we're talking about any of our household electronics or anything like that, any of the devices that I have here running this lecture currently, all of those are using a current generated by electrons. So we have a couple different things that go into this. We have, first, I'm going to start from the bottom actually. The electron current tells me how many electrons per second are moving through something. So for example, if I wanted to set up some little flagpoles. Oh, I'm still on eraser. That's why. Haha. If I set up some little flagpoles right here, right at the very end, and I'll have like my checkered flag and everything, right? Let's commit to the bit here. So here's my checkered flag. Here's my goalposts. The current that I have for the electrons is going to be telling me how many electrons pass through this goal in 1 second. So the units of that are a little bit strange. It's just per second. Technically, it's just per second, because electrons aren't real units to deal with, right? Electrons are not standard units like seconds or meters or anything like that. So even though we might say it's electrons per second, the real unit is just per second. But I'm going to keep writing it electrons per second because I think it's a little bit more intuitive. So how do they actually pass through that goal, though? Well, they have what we call a drift speed. So this whole motion right here, drift speed is not the motion as it's going along this path or along this path or anything else like that. Drift speed is what happens when I look at the average speed in the direction of my destination. So if I'm looking at this net displacement value, my net displacement over a period of time will give me my drift speed. How much of our speed is actually in a useful direction versus just randomly bouncing around. That's what drift speed is trying to tell us. So if we take that drift speed, we multiply it by the cross-sectional area of whatever wire or conductor that we're moving through, and we multiply that by another value called the electron number density, or the number density of free electrons, which is a value that depends on the material, right? So insulators, for example, will not have many free electrons, but conductors will have varying numbers of free electrons. And that's the number of electrons that are floating around because they are those covalent electrons and they're free to do whatever they want. But we have these three things. If you have seen anything with electric circuits before, electron current is not the same thing as the conventional current measured in amperes or amps. So keep that in mind. We'll talk about that soon, but it's not quite the same thing. Electron current is something a little bit more unique. So let's try this on a concept check real quick. Let's say that there is current traveling through some wire. If the wire diameter and the electron drift speed are both doubled by something, I don't know, but something doubles both of those quantities, what happens to the electron current? By what factor does it increase? Okay, so let's talk about it real quick. So what I've got here, if I write out this equation, number density times A times V of D. Now, number density depends on the material itself, right? Because it's dependent on those covalent electrons, it'll be different for every single conductor. Will have its own value for that. But we're assuming that it's going to be the same for each of these. So if I had an initial wire that had all of these quantities, and one of the things that I'll do real quick is I'll say, okay, well, I am told we have a diameter. That immediately sets off all of the red flags that I am dealing with a circle. So this will be N of E pi r squared times that drift velocity. Now, in our final case, we have expanded the wire. We have increased that drift velocity. So the electron current now, I have the exact same N of E. Pi is not going to do anything. If I double the diameter, I double the radius. So this will be 2r squared. And then I've doubled the drift velocity. I have 2 times 2 times 2. I should be increasing by a factor 8 when I've got something like that. Does that all make sense, though? Excellent. And I do appreciate the participation, by the way. Like it makes the whole thing a little bit easier for me. You know, when I know that stuff is getting through and you guys are are hearing things that I'm saying and everything else. It is much appreciated. All right. So now let's try it with maybe some bigger numbers here. And this will be a really fun one because this might be a little bit surprising. Don't be afraid if you find a strange number here. Let's say 10 to the 20th electrons flow through a cross-section of a 2 millimeter diameter wire. So again, that's another circle in the cross-section. But it's made out of iron, so the electron density is going to be this 8.5 times 10 to the 28th. But let's say that that number of electrons goes through in 5 seconds instead of 1 second. So what is the electron drift speed based on these quantities? And this is not an unreasonable thing that we might expect to see like any of our household circuits or anything like that. This is kind of these are some reasonable numbers for these things. We usually use copper instead of iron, but yeah, small differences, right? They've got the same number density for these. So go ahead and take a few minutes to work on this one. All right, how's about we start taking a look at this? And I forgot to create a new sheet. So just ignore that little blip right there. Let's go ahead and get ourselves set up with this thing. So this table has the only extra value that we actually need here, right? But what I'm looking for, electron drift speed, I've only really got one equation that I can use for all of this stuff, right? So we're going to start with that one. So I know that when I get into this thing, the electron current is going to be equal to the number density times the cross-sectional area times the drift velocity. Drift velocity being the thing that we're after. So before I can find that, though, I'm running into a couple of things. I don't know what a lot of these values actually are, not right off the bat. I'm going to have to pull that electron number density from that table that I've got. So that's an 8.5, there it is, 8.5 times 10 to the 28th. And this one is another one that's a little bit strange with units. What this is really saying is electrons per cubic meter, right? But once again, electrons are not a standard unit, so the per cubic meter thing kind of just sticks around. It's a number per cubic meter. So once we've got that, we also need to think about the fact that we have a 2 millimeter diameter. So diameter is equal to 2 millimeters, which immediately I'm going to convert that into a radius. Radius is going to be equal to 0.001 meters. And then the cross-sectional area will be pi r squared as that comes out. So the last thing that we've got, we also have the number of electrons. Number of electrons is equal to 10 to the 20th. That's not current density. Or not current density, that's not electron current. What we need to do is we need to take this, the number of electrons divided by the amount of time it took for those number of electrons to pass to get the electron current, right? Electron current is units of electrons per second. So we take electrons divided by seconds. Delta T is equal to 5 seconds. I know that this fraction looks a little bit strange at first, but that's okay. What we end up getting then is 2 times 10 to the 19th for that value. So once we have that number density, we can say, okay, let me just take this thing, plug in all the numbers that I've got so far. I will say the electron current divided by the number density times pi r squared will be equal to my drift velocity. Plug in all of those values, and are you ready for this very, very, very tiny value? Tiny as far as you might know, but this drift velocity is actually going to be 7.491 times 10 to the negative 5th meters per second. That's an accurate number. So in Canvas, this is asking for millimeters per second. Keep that in mind, right? But this is incredibly tiny. And at first you might think, okay, well, you know, it's maybe a bit smaller than I expected because I would assume that electrons move kind of fast because of how tiny they are. But let's compare this to something else real quick, right? What speed would they be moving at normally? If there wasn't a potential acting on them currently, then I would expect them to be moving somewhere around the average velocity, or VRMS. So let's find what VRMS should be. Let's try to compare this value. And if you're reading into the notes, this is one of the things that I do recommend solving out for as well. It's a fun little review, refresher on this value. But VRMS is going to be square root of 3 kBt over the mass of the electron. And let's just assume, I keep talking about household things, so let's assume it's room temperature or so. Let me say 300 Kelvin. It's a warm day. Plug in all those values. And I'll write that there so we're all clear. If T is equal to 300 Kelvin, what does the VRMS come out to be? A very casual 1.17 times 10 to the positive 5th meters per second. That is almost a 10 order of magnitude difference between the VRMS and the drift velocity. The reality of it is, the electrons are not very good at getting to their destination. Not very good at all. And before I go too much farther into this, I do want to start to look at another problem here real quick, just for a fun one here. I think it's a fun problem to look into real quick, because this is kind of a fun one. So let's take that same value that we just found for the drift velocity, right? So that's essentially the average speed of an electron moving through the wire. Take this to whatever room you're in right now. Look around, find the nearest light switch and what light it's going to turn on. So for me, I've got essentially something on the wall right over there, up to the light up in the ceiling. If you don't have a ceiling light, if you've only got a lamp, go ahead and use like the length of the wire of the lamp or something like that. But we're trying to calculate here, how long is it going to take for any of these electrons from the switch to the light bulb? How long is that going to take for them to travel that distance? So go ahead and stand up. If you've got a meter stick, I don't imagine you do in your room, but go for a rough estimate here, right? This is not any sort of, we don't have any sort of strict values we're looking for in this problem, but I'd like you to kind of guess what it would be given what the layout is in the room that you're in right now. Previously, when we were in the class, this kind of turned into a disaster because we did have meter sticks, but a lot of people would like to get up onto the tables to try and measure the length of the ceiling and other things like that. So try not to be too dangerous with it. But don't tell me if you are, because, you know, I can't see it, and I'm just going to trust that you're trying to be safe with whatever you're doing. But go ahead and try and measure out some of these values. It's not going to be a super crazy long problem or anything, but take a little bit of time. Calculate what these numbers ought to be. Convert it to a reasonable amount of time that you can easily conceptualize. And we'll see, we'll see what I mean in just a little bit. So take a few minutes to work on this one. Okay, so hopefully you've got some numbers and everybody's going to be a little bit different. Maybe within an order of magnitude is what we'll all get here. Right, so I'm estimating that in my room right here, as I've got it, it's maybe 2.5 meters up, 2.5 meters over. Right, and wires don't necessarily go directly that way through the wall, right? Sometimes they wrap around in different methods, but we're going for a bunch of estimations anyways, right? So for that kind of wire length, what would it actually take for the electron to get there on average? Because remember, we could get extremely lucky. What if the electron takes the fast track and manages to go like back and forth and just bounce in between the individual ones? Very unlikely, but technically possible. But let's go with the more likely scenario, the average speed, that drift velocity. Well, as I've got it, whoops, I wanted that to be in black, please. So let me say that I've got a velocity as we're going through this thing of 7.491 times 10 to the negative 5th, and a distance to cover of just 5 meters. Going back and forth between those two, take the distance divided by what that time should end up being, and I'm going to find something like 66,000. So that call this delta t is equal to the distance divided by velocity. In seconds, this is 66,746. Which just so happens to be exactly what somebody else in Twitch chat, or the Zoom chat had, of 18.54 hours. to get from the switch to the light. So, when you turn on lights in a room, do you typically wait 18.54 hours for the lights to come on? Or let's assume it's a shorter wire. Do you wait 6 hours for the lights to come on? I'm willing to bet no. And I feel like if anybody says yes, that's how long they wait, they're probably lying to me. And so let's think about what's actually going on here. Why do we instantly see the lights turn on, but the electron has to take so long to get from the actual switch? Well, the answer is that this entire time, all of these wires in the walls and everything else, they're electrically neutral, which is not immediately apparent why the light turns on immediately then, but let's think about this. This sea of electrons that's in a conductor, they're there the entire time. If I were to rip out some copper wire from my wall and disconnect it from the rest of the circuit, which first, don't just go cutting wires out of walls because you'll electrocute yourself, probably. But if I were to anyways, and I had that piece of wire in my hand, I would not find any sort of excess charge on that piece of wire, not positive nor negative. It would be electrically neutral. There would be a sea of electrons flowing through that thing still. But without any sort of potential difference, I wouldn't see any net movement of the electrons. But that's kind of beside the point. Then we can assume that the entire structure, all of the wires in the house or anything else like that, all of those are similarly electrically neutral. There are already electrons next to the light. Think about what happens to a hose. If I have like an external hose or something else, a hose outside, and I hook it up to a faucet and then I've got my nozzle on the very end. I turn on the faucet, I wait for a little bit, and then I start spraying water out the end of the hose. Is that the same water that just came out of the faucet? No, not quite, right? Because the water that just came out of the faucet's in that end of the hose over there. It has to travel throughout the entire hose before it actually gets to the nozzle, but water starts coming out immediately because there was already water there, and that water coming out of the faucet is pushing the water ahead of it, is pushing the water ahead of it, is pushing the water ahead of it, and so on and so forth, so that we get water instantly out the end of our hose as soon as we open that nozzle. The same thing happens with the lights. There's already electrons there. All of the electrons that start getting pushed when I flip the switch start pushing the electrons ahead of them. That net force, there's an electric field going through the entire conductor at that point, and it pushes the electrons that are already in the light as soon as the switch gets turned on. So it's a cool kind of thing. Now, sometimes if you actually deal with any electronics, sometimes there is a little bit of a delay. And that's not actually because the electrons have to travel, but it's usually some other factors. Sometimes it's inductance, sometimes it's temperature. There's a few different things that might cause a delay, but it's certainly not that the electrons have to take time to actually travel there. So just kind of a cool thing. I love those two problems back to back like that because you really get to look at kind of the almost unlikely scenario. What's going on with that drift velocity is, I think, surprising at first, and then maybe it's less surprising after you've seen that drift velocity that we're finding times like this, but, it's a cool little feature. So, that's all talking about what's actually going on inside of the conductors, right? Because the reality of it is that these atoms are huge in comparison to the electrons, and they actually are very, very tightly packed. This drawing is not a fantastic example of that, but the atoms are very, very tightly packed together. There's not actually a lot of free space between them. So with so many obstacles in the way, the electrons are going to have a nearly impossible time actually passing through them. Despite the fact that they're constantly buzzing around, finding a gap to slide through to the next layer is just, it's a task. It really is. And that's why we have such a low drift speed versus what the actual speed of the electrons are at any given moment. So, we can describe a few different things with this as well. We're not just limited to talking about the drift velocity. As long as we have an electric field being applied to this conductor, and that's applied, not a natural electric field, but as long as we have that electric field applied, then there's going to be the Coulomb force acting on the electron. There's going to be some acceleration pulling the electron towards the source of that electric field. And it's going to keep moving along like this until it hits something, and then its course gets diverted, and then it's going to feel that acceleration the same way again. And we get all of these little arcs as we go along, right? So we've got some other values that we can use to describe what's going on with this movement. Let's say we actually knew what the magnitude of that electric field would be acting on my conductor. Then I can redefine my drift velocity and therefore electron current by defining it instead of with these other values. I can define that drift velocity with a value called tau, the mean time between collisions. So how long it takes to get from this collision to this collision. How long it takes to get from this collision to this collision. And we're taking the average of all of those collisions, and we're finding out how long does it take for the electron to hit the next atom. Electron-electron collisions are technically possible, but because of the massive size difference between electrons and the atom collisions are going to be substantially more likely. So, and then we can just plug in that drift velocity into our equation for electron current, and we get a new form of the electron current just the same. So, let's take some of these ideas. Let's say that we have a pretty weak electric field, actually. 2 times 10 to the negative third volts per meter, which, remember, is the same as newtons per coulomb. But 2 times 10 to the negative third volts per meter electric field, and the electron current is 3.5 times 10 to the 17th. That's going through a 1 millimeter diameter aluminum wire, not aluminium. For the electrons in the wire, find the drift speed and the mean time between collisions. So use those brand new equations that we just found, and let's go ahead and calculate out what these values should be. It might help to define what these variables are as we're getting used to using them, because I know a lot of these are kind of new now. Okay, how's about we start to take a look at this one? So, as I've got it here, we need to figure out, or we need to pull from this table this electron density of aluminum. So that'll be a 6 times 10 to the 28th. We've actually got a lot of the details already kind of set up here for us. But it might be worthwhile. Let's go ahead and write out a lot of these things that we actually have given to us. So if we're flying back and forth between these things, we can start with number density just because it's aluminum. Before I forget about that, 6 times 10 to the 28th. And I'll go ahead and write out units for all of these things so we keep track of it. Electrons per cubic meter. But again, remember that the electrons are not a real unit, so it's just technically per cubic meter. But electrons helps me keep track. Hopefully it helps you keep track. All that good stuff. We also have a 1 millimeter diameter and 3.5 times 10 to the 17th electrons per second. I immediately, 3.5. 3.5 times 10 to the 17th. Again, electrons, not a real unit, but it helps conceptualize a little bit easier. Diameter is equal to 1 millimeter. I'm immediately going to convert that into a radius, which we're getting smaller and smaller here, 0.0005 meters. And then finally, we need that electric field, 2 times 10 to the negative third. Volts per meter, same as newtons per coulomb. Okay, so we need to find first the drift speed and then the mean time between collisions. So, and we're going to need to do this in that order too. So that'll help out a little bit here. Keep this nice and quick. But as we've got this thing, what I've got then, I'm going to start with my electron current equation. If I can draw anything at all. There we are. So my electron current equation is the number density times the cross-sectional area times the drift velocity. Drift velocity is the thing that we're chasing here. Area, as we know, is just pi r squared. Go ahead and write that out, though. Now that we've got all of that, let's solve this thing out for V of d. Number density, pi r squared. Got everything in there. Yep, plug those values in, and we should be expecting to find something kind of close to what we had found just for that last problem. Now I'm finding something like 7.427 times 10 to the negative 6th meters per second, which is not so far off from what we had just found. Okay, and once we have that value, going on to part B will be a little bit easier. I've got two different options. If I look at these equations again, both equations have tau showing up in them somewhere, but the electron current has a lot of different values, and I'm not feeling that. Let's just go ahead and use what the drift velocity equation says, because it's got a lot fewer things to keep track of. So that says that the drift velocity is equal to E Coulomb force divided by the mass that it's acting on times the amount of time, right? Acceleration times time gives us a velocity. That's where we get that equation. So with all that stuff in mind, then what we can say is, okay, let me rearrange this. I'm after tau V of d times the mass of the electron. I'll go ahead and write that out as one of our givens as well. Right, and that's coming from our constant sheet. And we also have the electron charge. And I'm going to say we don't need to worry about the fact that it's negative, because realistically what we're doing here, it doesn't make any sense to get a negative time. Right, this is kind of looking at the magnitude of the acceleration only, so the magnitude of the speed only. I'm not very interested in negative signs right now. So that's why we can kind of just safely ignore that one for the time being. E times E. All of this is equal to the mean time between collisions, tau. And when we plug all of that stuff in, we find, and this number shouldn't be that surprising, 2.114 times 10 to the negative 14th seconds. That's how long it takes between collisions that this electron experiences, right? And this actually shouldn't, it's a very, very small number, right? It's a very, very small number. But based on everything that we've been describing so far, with how tightly packed all of these atoms are, and the electrons at the speed that they're moving, this shouldn't actually be that surprising, right? A number like this kind of makes a little bit more sense. It fits this picture that we've been drawing so far when we're talking about how many collisions and how quickly the electrons are moving and how tight of a space they've got to move around in. All of those details factor into that number right there. Okay. But let's go ahead and keep looking at some new things then. So, conventional current. And I have an XKCD comic to go along with this one, because the rule of the internet is that for any situation, there is always a relevant XKCD comic. I'll give you a second to look at this one. This is actually kind of historically accurate. Benjamin Franklin was a big proponent in getting all of these equations about current set up in the first place. But it's one of the running jokes that we have in physics and electrical engineering and all of this stuff that we goofed up. And there hasn't really been a good fix for it. We run into this issue where the convention for current is actually backwards from what the typical flow of charge would be. And it's one of those things that all of our equations are set up at this point, so we kind of just deal with it. But it's kind of funny regardless. Because realistically, what happened here is we actually had a pretty good idea of what current and electricity and the Coulomb force was before we actually knew what was going on inside of atoms. Right? Before we understood what was providing that charge, we understood how charges interacted, which is kind of a strange order, but it means that we were doing a fair bit of guesswork for a time, trying to figure out where these things were coming from. Why does it pick up a negative charge? What is being transferred? What carries the charge? Right? Is it like some weird action that makes charge? Who knows? We didn't know. We didn't understand electrons and protons and all of those things quite yet. So we run into this issue where we have a value that we call conventional current, or just current, as we will typically call it, that goes opposite the direction of the electrons. It's a little bit confusing, I know, but basically what we've got here is that physically, whether a negative charge moves to the left or a positive charge moves to the right, they're equivalent. All of the effects come out to be the exact same as before. It doesn't actually make any difference that we got it wrong in the first place, right? It's the difference of a negative sign somewhere and everything else ends up working out just fine. But it is backwards from the electron current, and that's a little bit confusing. So, conventional current is actually, and I should probably make this a little bit bigger, but what it actually is, it's a flow of charge. So this definition right here is very important. It is how much charge per time gets moved. Right? So this is taking it like a derivative, assuming that it's constantly changing. But if we have a constant current going through something, if you plug in your coffee maker or anything else like that, that is going to have a constant current, you could just easily define that as I is equal to delta Q over delta T. That works out just fine. If we move 3 coulombs of charge in 3 seconds, that gives us 1 ampere of current, which we oftentimes shorten to just amps, right? If you think about a lot of the circuits in your house or something like that, if you've looked at the breaker box, there's 15 and 20 amp circuits, there's sometimes 30 amp circuits, all of things like that. That is this unit right here, conventional current, which I will soon just call current, but for the rest of the day, I'll try to keep calling it conventional current. So the transfer between those two is actually pretty easy though, because every single electron comes with the exact same amount of charge, right? 1.6 times 10 to the negative 19 coulombs means that if I multiply the number of electrons by the charge of the electrons, I get a charge, or if I multiply the rate of electrons times the charge of electrons, I get the rate of charge. So that's one easy way to transfer back and forth between the values that we have just been talking about with the conventional current that is standardly used. So let's try this. So a standard hairdryer might run on a 10 amp circuit, which does sound like a lot, but they actually do, they have a really high ampage. They're not super safe devices. But let's assume that I was trying to dry my hair with a hairdryer, and that has to take 2 assumptions. First of all, let's assume that it would only take 5 minutes to dry my hair. And second, we have to assume that I would even own a hairdryer in the first place. Neither of which are true, but for the sake of the problem, let's just assume. How many electrons would flow through that hairdryer if I ran it for 5 minutes? All right, how's about we start taking a look here? So, and again, this is kind of like a reasonable value that we would expect to see for some of these things. Certain devices in the house take a very high current, even though you might not necessarily expect them to. Hair dryers are a great example. Coffee pots are a fantastic example. Coffee pots actually use a ton of energy. They don't seem like it, but creating a hot plate uses a lot of energy, actually. So we have a conventional current of 10 amps, and we are going to run this thing for 5 minutes. Let me immediately convert that into our standard unit, 300 seconds. And then there's actually, there's 2 steps to take here, and we can do them in either order. But what I'm actually going to do is I'm going to start with my definition of what current actually is. Current is how much charge moves through in a certain amount of time. Delta Q over delta T. If I'm interested in finding how much charge moves through, I could rearrange this thing, and I could say, okay, well then delta Q, how much charge moves through is just the current times however long it's running. Doing that would find me 3,000 coulombs. And hold on for a second. Pause right there. Think about what I just said. 3,000 coulombs. Everything that we have dealt with so far has been microcoulombs at best. But these are real charges that we're dealing with now. We're moving a lot of charges all together at once, right? If we have been moving something, 17th, 18th kind of electrons at a time, that's the kind of numbers we're going to start to get. Right? We're getting into actual single-digit coulombs and everything else. But again, we're not just moving single charges here. We are moving many, 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 many charges all at once. So it's not that crazy. This is not all stacked into one point charge. This is a whole bunch of different point charges. Okay, so just kind of to level an expectation for what your units or what your value should be for a lot of these. So 3,000 coulombs, but then we say, okay, every single electron is contributing how much? 1.6 times 10 to the negative 19 coulombs. So if we're looking for the number of electrons, then we could say, okay, we'll just take that total charge divided by the charge per electron, and we will end up with the number of electrons at the end of the day. And when we plug in all of these numbers, we should find something like 1.875 times 10 to the 22nd electrons. So if you're looking for that answer in Canvas, the order of magnitude that we're looking for, it's this 22 right there. Again, Canvas spooks me sometimes with large or small numbers. So the order of magnitude was the thing that I was interested in. Now, there was another way to do this using the conventional equations that we've seen so far, but I wanted to bring this one up because it's fantastic to get that definition of current in there nice and early. The other way that we could have done this is we could have done the electron step first. We could have said that I know the relationship between current, conventional current, and electron current is just multiplying by E. So then the electron current would be I divided by E. And then all I would have to do is say, okay, well, that is my electrons per second. If I multiply the electrons per second times the number of seconds, I'm left with just the number of electrons, which we can see it's the same steps, but in reverse order. That's all it's doing. So, how do we feel? Do we have any questions or anything else? Oh, geez, a 3,000 Coulomb point charge. I don't know what would happen, to be honest. We have some handy-dandy calculators, don't we? That would certainly be a really, really strong electric field, wouldn't it? What would this do? Any positive charge, positive or negative charge in your body, how would that react? I'm trying to think. Ooh, better yet, how would that electric field react with a dipole or something? If it was 1 meter away from you, I would expect that that would be... Ooh, a very substantial force. I would imagine you would not be having a good time. That'll be my result. I'm going to assume pretty dead. If a 3,000 Coulomb point charge was very close to you, I would assume that you would be in trouble. Every charged particle in your body, if that was 1 meter away or something, every charged particle in your body would be experiencing something 10 to the 5th force, somewhere around there, which means that it would be experiencing an acceleration of, think on the order of 10 to the 30th meters per second squared. The neutral atoms in your body would probably be totally fine, but anything that has a charge or a slight polarization to it would suddenly be moving all over the place. So I don't know, though. I don't know what anatomically happens at that point. But yeah, it's a pretty crazy amount of charge. But then again, remember, so I think we might have, I don't remember if we ended up doing this problem initially, if it was one of the old problems, but if you stripped away all of the extra charges, how much charge that ends up being, but because everything is completely neutral, even if we are moving 3,000 coulombs of charge, there's 3,000 coulombs of charge coming up to replace that in just the exact same way, and the wire stays neutral the entire time. So it's a fun thing. It's a fun bit. All right. So let's keep going on with it. We've got just a couple more things for today. So there's one other thing that we've got that we can do with conventional current, and it's more of a stepping stone. Hang on here. So what do you mean? Does the electron hit you? Which part are you talking about here? I would imagine, so if you had are you talking about the 3,000 Coulomb point charge? I would imagine that would be stripping away a lot of charges, a lot of the electrons or negative charges from your body would get stripped out, but the positive charges blown out in some way. I don't know. That would be a pretty extreme amount regardless. But I don't know exactly what it would do. I don't know that we ever would be able to create that, well, maybe that much of a charge, but it'd be difficult. I guess it's technically possible, but it would be very difficult. You'd have to make sure you're far enough away from it. But anyways, so we've got one other quantity when we're talking about conventional current that we're going to kind of use here as a stepping stone. It'll have some different uses in different places, but it's the current density, and it's how much current is moving through a particular cross-sectional area. So the units for that are just amps per square meter, right? It's I divided by the cross-sectional area. Now, if we actually plug in some of these quantities, though, if we plug in like the current density not the current density, this is the thing we're using, the electron current and a few other things like that, we actually get this expression that looks a lot like it did for a current. But most importantly, when I'm talking about a stepping stone, a lot of the values that show up in this equation right over here give us a fun quantity, right? The current density for a particular material is equal to number density, charge of the electron squared times, tau divided by the mass. All of that plays into, that's material dependent, right? Those are not values that necessarily depend on anything else. What we're looking at right here, everything contained inside of this little blue section, is what we call the conductivity of a material. And the conductivity of a material is something that I think has been brought up multiple times in conversation, and you probably generally know that metals are conductive and glass is not conductive and things like that, right? I know I've talked about conductors and conductivity before in the context of thermal conductivity, and that's not actually super different. And in fact, it's a general rule of thumb that if something is a very good thermal conductor, chances are it's a good electric conductor as well. There's plenty of exceptions to that, but it's a general trend that we see a lot of the time. So in knowing that, we don't really have any idea what these units are yet. Ohms is a measure of resistance, which if you've done anything with electricity before, you will immediately recognize. But for anybody that's brand new to this, don't worry about it too much yet. Let's go with the conceptual understanding of these two quantities. Conductivity is how welcoming to current flowing through it is a material. Resistivity, which is the exact inverse of conductivity, is just how much does it resist having material or having current to pass through it. But we can use those quantities with some useful things. They are inherent to certain materials, and we will end up using those quite a bit more in the next chapter here. But for now, let's try and use some of these values. And we don't necessarily have to immediately use this brand new equation that we've got or these brand new equations, but it is helpful if we do. So let's say a 0.5 millimeter diameter silver wire has a current of 20 milliamps, which is reasonable for small electronics. In that wire, I'm looking for two different things. First, the electric field inside of the wire because of that potential difference. And two, the electron drift speed. All right, how's about we start to take a look at what we've got going on here? So, we've only got a couple of details here, but with what we've also got on the table, we'll have enough to end up solving this problem through. Let's go ahead and find ourselves a little bit of good space here. So this will be 27-5 as our whiteboard problem. And I'm going to pull some of these values off of the sheet as I've got it so far. So since we're dealing with a silver wire, I'm going to say, okay, we need the conductivity of 5.8 times, that's electron density. Conduction electron density materials. I saw the conduction and immediately jumped to it. Don't do the same thing. Conduction electron means the covalent electrons that are allowed to freely flow back and forth. So that's 5.8 times 10 to the 28th is our N of E. And again, I'll write that out as electrons per cubic meter. We're also going to need that conductivity value it'll really help. That's really what it comes down to. It'll really help us solve this a lot faster. For silver, 6.2 times 10 to the 7th. And that is per ohm meter, which is, again, is not a value that we know right now, but we'll talk about it very soon. Okay, the other things that we got is a diameter of 0.5 millimeters, and we just get smaller every single time, don't we? So let's convert that to a radius real quick. We've got 0.00025 meters. And lastly, we have that it is a 20 milliamp conventional current. Which let's go ahead and rewrite that immediately to 0.02 amps. Okay, a whole lot of information that we've got at this point. But here's what I'm thinking, right? I'm looking for the electric field. I'm looking for that drift speed. Those are the two quantities I'm after. I'm going to start with the electric field. What I can do, actually, is based on what we saw on the slide before this problem, this whole thing right here. Right, this whole mess of different values is actually just our value for conductivity, sigma. So we can write that the current density J is equal to sigma times the electric field. If we're after the electric field, we're most of the way there. Then we just have to say, okay, well, current density is actually I divided by the cross-sectional area A. We know that we are dealing with a circle because, again, we are given diameter. A is equal to pi r squared. Searching for E, go ahead and move it over. Electric field is equal to I divided by sigma pi r squared. If we plug in all of those quantities, we find 1.643 times 10 to the negative third volts per meter. And you might notice one of our other strange units here, we have been seeing a lot of very weak electric fields, and that's going to start to become a little bit more of a common deal. As we're dealing with a bunch of wall wires and everything else, we don't need super strong electric fields to start moving those charges along because there are so many charges to be moved. Right? And again, if we get really large electric fields, and that suggests really large potentials, and those really large potentials are dangerous to have in houses. So we top out at 120 volts in houses, in America at least, 220 in a lot of the rest of the world, but, you know, kind of that order, much above that starts to get very dangerous. And even that is kind of dangerous. We have to be careful with it. But anyways, that's our first quantity. Once we have that, we are looking towards getting that drift velocity. So what I can say is, all right, where does that show up? Well, it shows up in I of E. Right? The electron current is equal to that number density times cross-sectional area times the drift velocity. There's the drift velocity that we're after. Let me go ahead and just ramp that up to, let's multiply this entire thing by E, right? If we multiply I of E times E, then we just get conventional current. If we multiply the other side, well, there's not any sort of special value, but it just looks like this. Now I can solve this thing out. N of E, pi r squared, divided by E. We've got all of those values at this point. Go ahead and plug everything into that. We find 1.098 times 10 to the negative fifth meters per second. Another very small value, but that's kind of what we're expecting to see at this point. Yeah, it is small for an electric field, realistically, versus a lot of our point charges and everything else. What really we're going to find here is that for the most part, those 10 to the negative ninth Coulomb charges were actually pretty large for the time. Oftentimes, it's kind of difficult to isolate a whole bunch of charges like that because, again, the wires are electrically neutral, right? They don't have any sort of external electric field going out from them because they don't have any excess charge. So it just takes a little bit of an electric field to start pushing that electric, all of those electrons through the wire. And a lot of that, you might have to think about, like, how long is a wire going to be? How long is a wire going to be that's going around a house or something else like that? Let's assume, let me make an assumption here. N of E is one of the values from our tables. That's the electron density in different materials. I'm thinking of, like, if we have, say, 20 meters of wire from the breaker box going around, connecting back, say it's 20 meters of wire or something else like that. There's only 120 volt potential difference between those two, so 120 divided by that 20 is going to find 6 volt per meter as my electric field. Assuming that I'm not using it anywhere else, assuming all of that 120 is going into one spot in the wire. If it's just 20 meters long, which a lot of wires might be longer than that, we're still only going to expect to see a single-digit value for our electric field in that wire then. And then if it doesn't use all of that voltage, then it's going to be even smaller than that. So yeah, the time for very large electric fields will actually be mostly over for now. Okay, so I've got just a couple more things to talk about before we close out for the day here. But the first one is conservation of current. Can you destroy electrons without causing issues somewhere? No. If I have electrons go into one end of a wire, I better see the same number of electrons coming out the other end of the wire. That means that for the electron current, that's true. And by extension, the conventional current, it's also true. If a bunch of conventional current comes in, it's going to match exactly the conventional current coming out the other side. Right? If we're looking at any sort of junction, that's a little bit different, but it's kind of like this idea of, think about what happens with any sort of hose or anything like that, right? If I take a hose and it's got like a wide end on one side and a very shallow end on the other, or a very narrow end on the other, water comes in, water comes out. I can't get rid of water. The water inside of the hose, flowing through the hose at that rate, is going to be the same no matter where I'm looking. How fast it's moving will change though, right? And this is the basis behind those like cheap pressure washers. That it's taking essentially, how wide is a hose? Like a 3/4 of an inch wide tube and compressing it down to a very, 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 very tiny tube. The same amount of water is still flowing through, but to do that in a much more narrow tube, you have to accelerate the water to a much faster speed. Same thing here, right? The current density might change, the speed of the electrons might change, but the current has to be the same in and out, even if we fork it off into different paths, right? If I have a hose or a river or something else and that river forks out, if that river forks out, I still have the same amount of water that came to the fork. Now it's just split between these two. So that says that if I have current 1 and current 2, they're equal to current 3. Or if it's the other way, if I have current 1 splits into 2 and 3, then it's equal to 2 plus 3, as we've got all of those quantities. And to answer the question real quick, the difference between NE and J, electron density is not current density. Current density is how much charge is flowing through a cross-sectional area, whereas electron density is just how many free electrons are there in a material. How many electrons are there floating about, kind of like in this picture. These are electrons that are flying all the way around in every which way. That's what electron density is versus current density. So, let's try this idea out with a very quick concept check. I have a junction of 4 different wires all together, and we see the direction and the magnitude of the current going through each wire. Knowing our conservation of current, what is the current in the 4th unlabeled wire? All right, so here's what I'm going to do. I'm going to look at all of the currents coming in, all of the currents going out. I know that those two quantities must equal each other. Current in must be equal to current out. So, with that, let's look at everything coming in so far. 2 plus 5 must be equal to 9. It doesn't. Right? I want to make sure we're clear on that. It does not equal 9. So what we have to do, what we are missing an extra 2 amps on the input side to balance this equation. 2 amps coming in to the junction. We should be looking at 2 amps going to the left. Okay, I do want to start to look at this last whiteboard problem that we've got here. So in this case, what we have is like two separate wires spliced together. It's the same material the entire time, but the first part of the wire has a diameter of 1 millimeter. The second part of the wire has a diameter of 2 millimeters. Think about everything that we've had so far. What is the current? What is the electron drift speed in the second part, the 2 millimeter part of the wire? All right, let's go ahead and take a look at our last problem for the day here. Go ahead and paste this thing in there, and a few seconds later, my draw pattern is going to stop working or something like that, but how it goes, make it a little bit less scrunched down, something like that. Okay, so as we've got this thing, 27-6, what do we see here? Okay, part A. Easiest part of the problem. Current in is equal to current out. Current in, 2 amps. Current out, 2 amps. Done. That's it. Current in has to equal current out. The electrons have to go somewhere. They can't just disappear. Right? So anytime we see something like that, especially in this case, it's nice and easy because there's no other wires going off somewhere else. But anytime, even if we see a bunch of different wires, we know that everything going in has to come out somewhere. And that's how it balances out every single time. So finding that drift speed is going to be a little bit more challenging, though. Let's take what we know about what's going on with this current. So one of the equations that I came up with last time was that if we take the electron current, written out like this, then multiply both sides by E, what I get is conventional current is equal to N of E times cross-sectional area times V of D times the electron charge. Okay, well, this would work for us, except I don't actually know what that quantity, the electron density, is for this material. And I could go through the first wire and find it, but you know what? I'm slick and I'm also lazy, and those two things together means I'm going to try and avoid doing as much work as possible. So let's do this instead. Let me say that the current going through one must equal the current going through the other. So I'm going to call everything on this side labeled as 1, everything on the other side labeled as 2. I1 is equal to I2. N of E, because it's the same wire, or the same material in both cases here, the N of E is going to be the same. I'm going to rename the area to A1. I'm going to rename that drift velocity to V1, and the electron charge. Same material, same electron density, new area, new drift velocity, same electron charge. Cancels out, cancels out, cancels out, cancels out. I'm left with A1V1 is equal to A2V2. I am looking for V2, that drift speed in the second section of the wire. So I'm going to take A1 over A2. What do I see here? The diameter has doubled, which means the cross-sectional area has quadrupled. A1 to A2 is 1 to 4. Or you could go through and find those quantities, but again, slick and lazy. This is what we get. Knowing that, take V2, divide it by 4. What should we find? 5 times 10 to the negative 5th meters per second. I asked for that to be in purple, please. Try that again. There we are. All right, and that's it for that one. We will close out right there on our 27-1 lecture. Next time, we'll finish out the chapter.